And here a quiet contradiction arises, because the force that shapes the universe appears almost embarrassed by its own weakness, as if hiding behind the majesty it creates. Even a small magnet resting on a table can lift a paperclip against the entire gravitational pull of the Earth, exposing an imbalance so profound it feels like a cosmic riddle waiting to be solved. How can something so feeble orchestrate structures that stretch across millions of light years? Why would the universe entrust its largest responsibilities to its faintest force? These questions linger like a slow echo, drawing us deeper into mystery, because the answer may challenge our most basic assumptions about how reality holds itself together. And here the story bends, inviting us to reconsider gravity, not as a familiar companion, but as an enigma across the observable cosmos. Gargantuan clusters of galaxies drift within invisible wells of gravitational influence, moving with a patience that borders on ancient ritual. Yet, the force guiding them acts with a delicacy so faint that individual atoms barely acknowledge its presence. This contradiction creates a tension at the heart of physics, suggesting that gravity belongs to a domain where subtlety triumphs over strength. Perhaps it is not weak in the way we imagine, but instead diluted across more dimensions than our senses can perceive. Or maybe its softness is a clue that the universe values balance over dominance, allowing certain forces to roar while gravity merely hums. Here, a deeper problem emerges, hinting that our understanding rests on foundations that may not be complete. As we descend to the human scale, gravity seems even more modest, pressing us gently toward the ground, shaping our steps, guiding the fall of a tossed stone. Its presence feels dependable, almost domestic, as if it were simply part of the world rather than a fundamental expression of cosmic structure. Yet the more closely we examine it, the more its strangeness begins to glow beneath the surface. Why does it refuse to match the strength of the electromagnetic or nuclear forces? Why does it act universally on all mass yet remain so astonishingly inefficient? These questions drift like silent constellations, pointing toward a truth that has not yet fully revealed itself, and inviting us to consider whether gravity's softness masks an undiscovered principle woven into space-time. Perhaps gravity's weakness is not a flaw, but an intentional feature of a universe that balances expansion and collapse with exquisite care. If it were only slightly stronger, stars would burn too quickly, planets would crumble under their own weight, and the delicate chemical processes that foster life would never arise. If it were weaker still, galaxies would drift apart before they ever formed, leaving a cosmos barren and cold. This fragility suggests a deeper symmetry, an equilibrium that whispers of hidden dimensions or unseen mechanisms shaping space-time beneath our awareness. And here the thought sharpens, because the softness of gravity may be the very clue that leads us toward a more complete understanding of reality, one in which the universe's faintest force reveals its most profound secret. Gravity's weakness becomes more than a curiosity when placed beside the other forces that govern the universe. The electromagnetic force binds atoms with an intensity so fierce that a spark of static electricity can overpower the pull of an entire planet. The strong nuclear force fuses the hearts of stars, holding quarks together with unimaginable ferocity. Even the weak nuclear force, subtle though it seems, shapes the alchemy of radioactive decay that seeds new elements across cosmic time. Against these giants, gravity feels almost spectral, a faint pull that acts everywhere yet rarely dominates. And here the hierarchy problem emerges, not as a technical inconvenience, but as a chasm in understanding that whispers of something unfinished beneath the laws of nature. Physicists measure forces not only by their effects, but by the energies at which they become unified or distinct. At the quantum scale, the strong, weak, and electromagnetic forces dance with extraordinary vigor, interacting through particles that exchange momentum in sharp bursts of energy. Gravity, however, remains aloof, participating with a shyness that seems entirely out of place in such an energetic arena. If one imagines each force as an instrument in a cosmic orchestra, gravity appears as a distant flute whose notes barely register, yet somehow define the rhythm of the entire performance. This imbalance is so extreme that it invites suspicion, as if the universe is hinting at a mechanism our current theories have not yet uncovered. The hierarchy problem confronts us with a number so vast it borders on the absurd. Gravity is weaker than the strong nuclear force by a factor of 10 followed by 38 zeros, a disparity so immense it seems to defy the logic of a universe built on consistency. Why should nature allow such disproportion? Why would one force dominate the quantum world while another dominates the cosmic? And here a deeper tension emerges, because if gravity were only slightly stronger, stars would collapse under their own weight, burning too hot and too briefly for life to arise. Yet if it were weaker, matter would drift without cohesion, preventing galaxies from forming at all. This suggests a balancing act so delicate it feels almost deliberate, as if the universe tuned gravity's softness with exquisite precision. Some physicists suspect that gravity's weakness might be the shadow of unseen dimensions folded tightly into the fabric of space-time. Perhaps gravity is not intrinsically faint, but instead diffused across realms we cannot perceive, leaking into hidden corridors of reality, while the other forces remain confined to the familiar three-dimensional world. If so, what we experience would be only a faint residue of a more fundamental interaction, its strength diluted by a geometry that escapes human senses. And here the story bends, because this idea implies that our universe may be layered, with gravity penetrating deeper than our instruments can follow. Others propose that unknown particles, still undiscovered, may mediate gravity in ways that soften its influence on the scales we observe. These hypothetical entities, whispering between dimensions or oscillating through fields yet unmeasured, could hold the key to explaining why gravity resists unification with the other forces. But this possibility also carries a quiet unease, because it hints that our entire model of reality might be incomplete, a veneer covering deeper structures waiting to be revealed. In this sense, the hierarchy problem becomes a doorway, pointing toward a frontier where physics meets philosophy. Yet another perspective suggests that the hierarchy itself may be essential, a fine-tuning that allows complexity, stability, and life to emerge from the cosmic sea. What appears to be a weakness might instead be the universe's most profound strength, a subtle calibration that lets matter gather without crushing, burn without exploding, and evolve without disintegration. If this is true, then gravity's softness is not an accident, but a clue, guiding us toward a more expansive understanding of how the universe holds itself together, and why it chose such delicate proportions to do so. At the smallest scales of existence, the world behaves like a restless dream, particles flicker in and out of being, probabilities replace certainties, and every interaction is governed by quantum forces so intense that a single exchange of energy dwarfs the pull of entire planets. This is the realm where quarks tremble, where electrons orbit not as bodies tracing paths, but as clouds of possibility, where fields ripple with fluctuations that never truly settle. And yet, when we look upward to the stars, everything feels different. Gravity smooths the chaos into elegance, shaping planets with quiet patience and guiding galaxies along arcs that seem almost choreographed. Here a contradiction appears, delicate yet profound. Because the universe is held together by two laws that refuse to speak the same language. Quantum mechanics describes a world of abrupt jumps, discrete packets of energy, and wild uncertainty. General relativity describes a world of continuous curves, flowing geometry, and space-time bending like a living fabric. Each theory has been tested with extraordinary precision, and each dominates the domain it was crafted to explain. But they cannot be combined into a single framework without tearing at the seams. And this is where gravity's weakness becomes more than a curiosity. It becomes the quiet barrier that keeps the quantum from overwhelming the cosmic. If gravity were only slightly stronger at small scales, its influence would distort the quantum world beyond recognition, collapsing probabilities into singularities and destroying the delicate mathematics that allow particles to exist at all. Physicists have long attempted to quantize gravity, to treat it the way we treat electromagnetism or the nuclear forces, but the effort dissolves into paradox. If the graviton exists, the hypothetical quantum particle of gravity, it would interact so feebly that it becomes almost undetectable, a ghost among the already invisible. The slightest breath of energy in the quantum realm would dwarf its effect, burying its presence beneath the roar of stronger forces. Yet without a quantum description of gravity, our understanding remains divided, as though the universe carries two manuscripts written in incompatible alphabets. At the heart of this incompatibility lies the Planck scale, a threshold so extreme it feels almost mythical. It represents the point where quantum energy becomes so concentrated that it warps space-time itself, where the geometry described by relativity collapses under the violence of quantum fluctuations. To reach this scale requires energy so vast that even our largest particle accelerators barely scratch the surface, revealing a gulf between gravitational and quantum forces so enormous it defies intuitive comprehension. And here, a deeper problem emerges, because the Planck scale is where a true theory of everything must reside. Yet it remains sealed behind magnitudes of weakness that gravity refuses to surrender. As we shift from the micro-world to the cosmic panorama, the dissonance becomes even sharper. Quarks bind with a fury measured in trillions of electron volts, while galaxies drift with a softness that barely registers at the particle level. The smallest particles whisper with quantum noise, while the universe shouts with gravitational structure. And somehow these two voices must coexist without ever harmonizing. This imbalance suggests not randomness, but intention, as if nature designed a separation to keep the quantum world free from gravitational turbulence, preserving a space where probability could flourish, uncrushed by the weight of space-time. Some researchers suspect that gravity resists quantization because it is not fundamentally a force at all, but a property of geometry emerging from deeper layers of reality. Others propose that gravity is diluted across extra dimensions, its strength spread thinly through spaces we cannot perceive, leaving only a faint residue detectable in our familiar three dimensions. In this view, gravity's weakness is not a flaw, but a clue, a softness that hints at a hidden architecture beneath the fabric of existence. And here the story narrows into a quiet cliffhanger. Because if gravity is spread out across realms we have yet to detect, then its refusal to fit the quantum puzzle may be the very sign that points the way toward a deeper, more unified universe waiting beyond the limits of our understanding. Among the most startling ideas in modern physics is the possibility that gravity appears weak, not because it is fragile, but because it pours itself into dimensions beyond our sight. In this view, our familiar universe becomes a three-dimensional membrane suspended within a grander arena, a higher dimensional expanse, often called the bulk. The other forces cling tightly to this membrane, unable to wander, but gravity alone roams freely, its influence spreading outward through unseen corridors of reality. And here a quiet shiver arises, for if gravity can escape our world, then perhaps our cosmos is only a thin surface upon a deeper cosmic sea. The hidden dimensions hypothesis emerges most vividly from string theory, a framework that replaces point-like particles with trembling one-dimensional strings whose vibrations create the spectrum of matter and force. These strings require additional dimensions for their mathematics to remain consistent, suggesting that our universe may be woven into a structure far more intricate than its visible forms imply. In some versions, our membrane floats beside countless others, each a separate universe with its own laws, drifting through the higher dimensional bulk like luminous sheets. If gravity ripples through this vast arena, its strength would diminish as it diffuses, explaining why it reaches us as a faint residue. Yet this possibility carries both wonder and unease, for it implies that events in neighboring dimensions might subtly tug upon our world, leaving gentle imprints we have not yet learned to measure. Brain-world cosmology extends this vision further, portraying our universe as a dynamic sheet capable of bending, vibrating, or colliding with others across the higher dimensional expanse. In such a scenario, gravity becomes a messenger between realms, its lines of influence stretching beyond the limits imposed on the strong, weak, and electromagnetic forces. These other forces, confined to the membrane, shape chemistry, atoms, and life with fierce intensity. But gravity's freedom dilutes its strength, allowing it to roam into the vastness beyond. This imbalance may be the signature of a deeper architecture, a cosmic scaffolding where geometry and force intertwine across dimensions our senses cannot perceive. Yet here, a new tension forms, because if gravity can drift into the bulk, then forces from the bulk might drift back, subtly shaping phenomena we mistake for dark matter or unexplained cosmic patterns. Such possibilities blur the boundary between the known and the hidden, suggesting that the universe surrounding us is only a fragment of a grander, multi-layered reality. To contemplate hidden dimensions is to confront a blend of beauty and vertigo, for it implies that the space we inhabit is not the full stage of existence, but merely the foreground of a deeper cosmic tableau. If gravity can seep through these additional dimensions, its apparent weakness becomes a clue rather than a flaw, a sign that the true arena of physical law stretches far beyond what our instruments can touch. Some theories imagine dimensions curled tightly upon themselves, so small that even our most precise detectors cannot probe their chambers, while others envision broad expanses where whole universes drift like islands across an unseen ocean. In either case, gravity's ability to wander suggests that our reality is porous, its boundaries open to influences we have yet to understand. And this is where the thought sharpens, because if hidden dimensions indeed lie closer than breath, then every gravitational ripple we feel may carry echoes from realms adjacent to our own. Such a possibility transforms gravity into a bridge between worlds, a faint thread connecting the familiar to the unseen. It also leaves us with a lingering unease, for it implies that our universe may not be solitary, but part of a vast hierarchy of structures woven into the bulk. Yet within this unease rests a quiet exhilaration, the sense that by following gravity's soft trail, we are approaching a doorway into a deeper architecture of reality, one that may reshape our understanding of existence itself. If gravity has a particle, it would be the quietest messenger in the universe. The graviton, long predicted but never observed, is thought to carry the subtle pull that binds stars and shapes galaxies. Yet its interaction would be so weak that even a detector the size of Earth would scarcely register its presence. This near invisibility is not a flaw in our instruments alone. It is a reflection of gravity's strange nature, a force that governs the grandest structures while whispering through the smallest scales with almost no trace. And here a subtle unease arises, for it suggests that gravity may operate on a level deeper than the particles we know, belonging perhaps to a realm that does not conform to the usual language of quantum fields. The contrast becomes sharper when we turn to gravitational waves, ripples in space-time birthed from some of the most violent events in the cosmos. When black holes spiral into each other, when neutron stars collide with crushing intensity, the universe trembles with waves that spread in all directions. Yet, by the time they reach Earth, these waves distort space-time by less than the width of a proton. It took humanity a century after Einstein's prediction to detect even the faintest signal, using lasers bouncing across kilometers of vacuum in instruments so sensitive they could measure the drifting of atoms. That such colossal events produce waves so gentle speaks to gravity's dual identity. Ferocious in origin, feather-soft in arrival. This gentleness raises deeper questions. Why should a merger of black holes, objects whose gravity is so extreme they trap even light, produce waves that barely disturb the fabric they traverse? Why does the cosmos seem to hide the footsteps of its most dramatic moments behind a veil of quiet? Perhaps the answer lies in the graviton's reticence, for if gravity is carried by such a particle, it must couple so weakly to matter that it passes through worlds unnoticed. Here a new tension forms, because if the graviton is nearly undetectable, how can we ever confirm its existence? And if we cannot, what does that mean for our quest to unite quantum mechanics with general relativity? Some physicists speculate that gravity's weakness is a sign that it may not be fundamental at all. Instead, it could be an emergent phenomenon, arising from deeper principles the way temperature arises from molecular motion or pressure from statistical behavior. In this view, space-time itself might be a kind of collective effect, and gravity a byproduct of information, entropy, or geometry emerging from hidden microscopic rules. If true, the graviton would be less like a basic particle and more like a vibration in a vast underlying structure. Not fundamental, but emergent. Not primary, but derivative. Yet this idea also brings a quiet discomfort, for it implies that the universe hides its most basic fabric behind levels of description we have not yet unraveled. Other theories propose that gravity spreads across extra dimensions, diffusing its influence so widely that its quanta become nearly impossible to capture. The graviton, free to wander beyond our familiar three dimensions, would appear feeble because only a fraction of its presence remains within our universe. This possibility blurs the line between detection and impossibility, suggesting that the graviton may always escape our grasp, not because it is non-existent, but because it belongs partly to worlds we cannot perceive. And here the story bends once more, because the faintness of gravitational waves and the ghost-like nature of the graviton may be clues pointing toward a deeper architecture underneath space-time. In the end, gravity's messenger remains elusive, its whispers scattered across the cosmic ocean. Whether the graviton exists as a particle, a vibration, or merely a hint of an emergent order, its silence challenges our understanding of what is fundamental. It leaves us with the unsettling thought that gravity may not behave like the other forces at all, and that its softness may be the signature of a deeper reality waiting to be uncovered. There is a more unsettling possibility hiding beneath the familiar frameworks of physics, one that shifts the ground under our feet and dissolves the very fabric we think we inhabit. It suggests that gravity may not be a force at all, but an illusion emerging from deeper laws, an echo of information rearranging itself across the universe. In this view, space-time is not fundamental, but constructed, a smooth geometry rising from countless microscopic bits of data interacting beneath our awareness. And here, a quiet vertigo begins to form, because if gravity is emergent, then the weakness that has puzzled physicists for centuries becomes a natural consequence, the soft afterglow of a deeper, statistical order shaping the world from below. Entropic gravity proposes that what we perceive as gravitational attraction is actually the universe seeking equilibrium, a thermodynamic tendency rather than a fundamental pull. Particles drift toward one another not because of an invisible force, but because the underlying information prefers configurations of greater entropy. Gravity, then, becomes a kind of cosmic bookkeeping, the large-scale behavior of systems adjusting toward balance. This perspective reframes the universe not as a stage upon which forces act, but as an information engine where geometry and motion arise as collective properties. And this raises a chilling question. If gravity is only the shadow of statistical behavior, how much of our reality is merely an emergent pattern rather than a fundamental truth? The holographic principle extends this idea with even more dramatic implications. It suggests that everything within a volume of space, every atom, field, and ripple of energy, can be described entirely by information encoded on the boundaries surrounding it. Our three-dimensional world may be a projection of data inscribed on a distant surface, much like a hologram, whose depth is an illusion created by intricate interference patterns. In such a universe, gravity would emerge naturally as a reflection of how information is arranged on this boundary, a gentle bending of space-time that arises from deeper computational rules. Yet this possibility also carries a sense of disquiet, because it implies that space itself is only a convenient illusion, a construct built from information that never truly resides where we think it does. Emergent space-time theories push even further, proposing that time, distance, and dimensionality appear only when vast networks of microscopic bits linked together in particular ways. These networks behave like a woven fabric, where the smoothness of space-time is the large-scale texture of countless connections. In this framework, gravity becomes a byproduct of how these connections stretch, compress, or rearrange as information flows across the network. Its softness is not the sign of a weak force, but the consequence of an emergent property, a gentle ripple atop a profound ocean of hidden structure. And here the story bends, because if space-time itself arises from something deeper, then our most basic intuitions about motion, location, and existence may be shadows cast by mathematics we have not yet glimpsed. Such ideas evoke both awe and unease. Awe, because they hint at a universe whose elegance surpasses even the boldest theories. Unease, because they suggest that what we experience as reality may be no more fundamental than the warmth that emerges from a swarm of molecules. If gravity is emergent, then the universe is not built from forces acting through emptiness, but from patterns of information weaving themselves into the geometry we inhabit. This reframes weakness not as deficiency, but as revelation. Gravity is soft because it is secondary, a consequence rather than a cause. Its faintness is a clue pointing toward a hidden layer beneath the world, a layer where equations give birth to space, where statistics generate time, where information sculpts the illusion of solidity. And this is where the tension settles most deeply. If gravity is emergent, then the universe we know is not the universe that is. Beneath the quiet arcs of planets, beneath the shimmering web of galaxies, beneath the space-time that seems so solid, lies a realm of pure information, whispering the rules that give rise to everything we see. In following gravity's softness, we may be approaching the threshold of that unseen layer, drawn toward the realization that reality is far more subtle and far more mysterious than the world our senses reveal. The universe is not merely expanding, it is accelerating, stretching itself with a quiet urgency that no known force can fully explain. This cosmic quickening, attributed to the mysterious presence of dark energy, turns gravity into something almost tragic. A sculptor whose hands grow weaker as the canvas beneath them pulls away. Galaxies that once drifted apart at gentle speeds now recede with increasing haste, carried by the swelling fabric of space. And here a troubling paradox emerges. The force that binds stars and worlds appears powerless before a repulsive energy woven into the universe itself, an energy that urges everything toward separation. Gravity, already the faintest of the forces, becomes even more fragile when placed in the shadow of dark energy's vast and unexplained influence. The accelerating expansion transforms the cosmos into a quiet battlefield where gravity fights a losing war. On the scale of galaxies and clusters, it pulls inward with delicate persistence, trying to maintain cohesion in a universe that wishes to tear itself apart. Yet, on the largest scales, dark energy dominates, pushing galaxies beyond one another's reach, ensuring that the distant universe grows colder and more isolated with time. This tension reveals something deeper about gravity's weakness. It is not merely a curiosity of nature, but a necessary trait that allows the universe to evolve in the way it has. If gravity were even slightly stronger, the early cosmos would have collapsed into dense clumps, stars would have ignited with violent urgency, and the delicate balance needed for life would never have formed. If weaker, It would have been overwhelmed by expansion long before galaxies emerged. In this sense, gravity's faintness becomes a crucial tuning, a soft note that allows complexity to bloom in a universe shaped by both attraction and repulsion. Dark energy intensifies this paradox. It acts uniformly, permeating all of space with a repulsive pressure that increases as space itself expands. Gravity, by contrast, weakens with distance, its influence thinning across the cosmic gulf. The result is a growing asymmetry. The more the universe expands, the more dominant dark energy becomes, and the less capable gravity is of holding distant structures together. Some physicists wonder whether this signals an inevitable future in which gravity's role diminishes further, its voice fading as cosmic expansion accelerates toward an unknowable horizon. Here a subtle dread arises, because it suggests that the universe may one day slip beyond the reach of the very force that once shaped its grandest designs. Yet there is also beauty hidden in this imbalance. Gravity's weakness allows pockets of order to form amid a universe trending toward dispersal. Inside galaxies, its gentle pull gathers matter into stars, whose light warms planets and seeds chemical reactions. Across billions of years, this quiet persistence carves islands of structure in a sea of increasing emptiness. Without dark energy, the cosmos might have collapsed under its own weight. Without gravity's softness, it might have remained too diffuse for anything meaningful to form. Their interplay, one pulling, one pushing, creates the fragile middle ground in which observers arise to contemplate the forces shaping their existence. This raises a profound question. Is gravity weak because it must be for life to emerge? The idea borders on philosophical, yet the evidence whispers in its favor. A universe where gravity matches the strength of the other forces would be short-lived, violent, and barren. A universe where it is much weaker would drift without structure, unable to gather the matter needed for stars or planets. Our reality sits delicately between these extremes, tuned to a narrow window where complexity can flourish. And here the tension deepens, because the accelerating expansion hints that this balance is temporary, a fleeting equilibrium in a cosmos whose long-term trajectory slips steadily toward emptiness. We find ourselves in a universe governed by softness and repulsion, where gravity's weakness is not a flaw, but a quiet triumph of cosmic balance. Dark energy pushes outward, gravity gathers inward, and between these competing tendencies lies the narrow possibility of worlds, biospheres, and consciousness. In the faintness of gravity, we may see the very reason we exist. A softness that allows the universe to breathe, to expand, and to create the delicate structures capable of asking why it is this way at all. If gravity were only slightly stronger, the universe would fold into itself with ruthless efficiency. Clouds of gas would collapse before they could fragment, forming black holes instead of stars. Matter would rush inward too quickly for delicate processes to unfold, igniting brief, furious bursts of fusion that extinguish themselves almost instantly. Planets would be crushed beneath their own weight, or never form at all, swallowed by the gravitational tides of stars that collapse and flare in violent cycles. In such a universe, complexity would be an unfulfilled dream. The cosmos would move too quickly, burn too brightly, and collapse too completely for anything like life to emerge. And here a quiet dread settles in, because the difference between our universe and this catastrophic one could be no more than a gentle shift in a constant we rarely question. If gravity were slightly weaker, the opposite tragedy unfolds. The early universe would expand too rapidly for matter to gather. Galaxies would be pale, diffuse structures, their stars drifting too far apart to influence one another. Many stars would fail to form entirely, as gravity's feeble pull could not coax atoms into dense cores. Those that did ignite would be scattered across an emptier cosmos, isolated and rare, leaving no foundation for planets to orbit or chemical cycles to develop. A weaker gravity universe would feel cold, thin, and unstoried. A cosmic expanse with motion but no meaning, structure but no evolution. Its silence would not be serene but barren, echoing with what could never be. And this reveals a deeper tension. Too strong and the cosmos burns, too weak and it never lights. Between these two extremes lies a razor-thin valley, where stars ignite with steady warmth, planets condense with patient grace, and chemistry unfolds at humanly comprehensible tempos. This narrowness is startling. A slightly stronger gravitational pull would shorten stellar lifetimes to mere millions of years, far too brief for evolution to find footing. A slightly weaker pull would prevent heavy elements from forming in stellar cores, leaving the universe composed mostly of hydrogen and helium, incapable of crafting the complex molecules life requires. Every step toward strength erases stability. Every step toward weakness erases possibility. That we inhabit the midpoint feels improbably fortunate, as though reality tiptoes across a tightrope suspended over cosmic emptiness. Even galaxies, the vastest structures bound by gravity, depend on this fine balance. With stronger gravity, galaxies would collapse inward, tearing themselves apart in violent, unstable flows. With weaker gravity, they would fail to coalesce, their stars too diffuse to form the spiraling patterns we observe. The Milky Way itself is a monument to gravity's precision, a structure that exists only because the force that shapes it is neither too fierce nor too faint. One cannot help but wonder, why does gravity sit so delicately within this life-permitting window? Why does the universe operate at exactly the threshold where beauty can arise? Such reflections lead to a haunting question. Is this fine-tuning a coincidence, the blind outcome of an indifferent cosmos rolling the dice across a landscape of possibilities? Or does it hint at a deeper necessity, a hidden principle that selects for universes where order can emerge from chaos? Some theories suggest a multiverse, an infinite ensemble of universes, each with its own laws, in which we simply inhabit one of the rare havens where gravity's weakness aligns with the conditions required for observers to exist. Others propose that gravity's tuning is not accidental at all, but woven into the deeper structure of reality, shaped by mechanisms we have yet to uncover. Whatever the explanation, the fragility of this balance is impossible to ignore. A universe with slightly stronger gravity collapses into darkness. A universe with slightly weaker gravity drifts into emptiness. Our universe, this narrow, improbable island between two cosmic abysses, feels almost intentional in its delicacy. And here the thought lingers, suspended like a soft echo. Perhaps gravity's weakness did not merely allow our reality to exist. Perhaps it selected it. Gravity's weakness invites us into a quieter realm of reflection, one where physics and philosophy begin to blur. For all its scientific strangeness, the fine-tuning, the dilution, the mismatch with quantum laws, its gentleness carries a deeper resonance. The universe could have been governed by overwhelming forces, by relentless strengths that crushed structure as soon as it began to form. Instead, it chose fragility. It chose a force so soft that it takes entire planets, stars, and galaxies to reveal its presence. And here a question emerges, subtle yet profound. Why does reality favor delicacy over domination? Ancient thinkers searched for first principles long before modern physics emerged. Aristotle spoke of causes and essences, the underlying truths that give rise to form and motion. Eastern traditions imagined balance as the foundation of existence, a harmony between opposing tendencies rather than a battle of competing strengths. Gravity's faintness seems to echo these old intuitions, suggesting that creation is less an act of force and more an unfolding of equilibrium. A universe built on overwhelming power would be brief and chaotic. A universe built on gentleness allows time, structure, and consciousness to bloom. Perhaps weakness, not strength, is the true architect of order. Modern cosmology complicates this philosophical instinct, yet it also deepens it. Gravity's softness is not merely a requirement for stars and galaxies. It may be the very reason any form of complexity exists. A stronger gravitational pull would erase the delicate gradients needed for atoms to gather and ignite. A weaker one would disperse matter so thoroughly that the cosmos would be barren. We find ourselves in a narrow corridor where existence feels not only structured, but improbable. This realization carries both awe and unease, because it hints that the universe we inhabit is perched on the edge of impossibility, held together by a force that barely asserts itself. In this sense, gravity's weakness becomes a message, not in a mystical sense, but in a philosophical one. It suggests that reality thrives not through overwhelming influence, but through carefully tuned relationships, through constraints that allow openness rather than collapse. The cosmos is not built on brute strength, but on the subtle interplay of forces balanced with astonishing precision. Weakness becomes a form of permission, a space in which stars can endure, in which life can take root, in which minds can wonder about their origins. And this reframes the entire cosmic story. Fragility is not an accident, but a condition that makes meaning possible. Some philosophers argue that the laws of nature reveal the character of the universe, that the patterns governing physical processes reflect deeper truths about existence. If so, gravity's faintness may suggest that creation prefers the slow, the gradual, the sustained. It may hint that stability requires softness, that endurance emerges from restraint, that the most profound structures are those allowed to evolve gently rather than forced into shape. Even at the grandest scales, the cosmos seems to favor patience over power. Yet beneath this poetic resonance lies a sharper question. If gravity's weakness is so essential, so carefully placed between extremes, then what does that say about the deeper structure of reality? Is this fine-tuning merely a fluke in a multiverse of endless variations? Or does it arise from a principle we have not yet grasped, a truth that binds mathematics, information, and space-time into a coherent whole? The discomfort grows when we consider that the laws allowing us to exist may themselves be traces of something beyond our universe, echoes of hidden mechanisms that shaped the constants long before galaxies formed. Gravity's softness might be telling us that the universe is not an arena of brute competition, but a tapestry woven through balance, restraint, and fragility. It may be less a force and more a reminder that existence requires tenderness at every scale. And yet, just as this idea offers comfort, it also opens a deeper mystery. If gravity's weakness is meaningful, what future truth lies behind it? What deeper layer of reality waits to be uncovered, encoded in the gentle pull that shapes stars, guides planets, and holds all living things lightly to the surface of a fragile world? Gravity's weakness has carried us through a labyrinth of ideas, a journey that began with a whisper beneath our feet and expanded outward toward the edges of the visible cosmos. At first it seemed like a flaw, an inexplicable mismatch, a force too gentle to belong among the giants of nature. Yet as each layer unfolded, this softness revealed itself not as an error, but as a clue. Hidden dimensions, emergent space-time, quantum resistance, cosmic fine-tuning. Every path we followed led to the same quiet revelation. The universe is deeper than it appears. Its foundations lie not in brute strength, but in subtleties so delicate that only a force as faint as gravity could hint at their presence. And here the thought begins to sharpen, because weakness in this context becomes a kind of signature, an imprint of an architecture more intricate than our minds can fully grasp. In the framework of extra dimensions, gravity's gentleness suggests it may wander beyond the boundaries of our world, slipping through geometric corridors we cannot perceive. Its faintness becomes the trace of a freedom the other forces lack, its dilution a sign of higher spaces pressing against the edges of our own. In emergent theories, gravity's softness arises from the collective behavior of microscopic information, a quiet consequence rather than an originating cause. Its weakness is not deficiency, but emergence, a force that appears only when deeper layers of reality align into larger structures. Even in multiverse speculation, gravity's faintness becomes meaningful, a requirement for stability within the narrow band where galaxies, chemistry, and observers can arise. These ideas differ in form, yet share an underlying truth. Each suggests that what we see, space, time, force, matter, is not the whole of reality, but the surface of something far more profound. Gravity's weakness becomes the common thread, the gentle reminder that the laws shaping our cosmos may be shadows of deeper principles. Its softness is not a scientific inconvenience, but a philosophical invitation, urging us to look beyond the scales we know. And in this realization, the tension that has followed our journey shifts from confusion to anticipation. As though gravity is pointing toward a horizon we are only beginning to discern. When we consider the cosmic expansion driven by dark energy, gravity's faint pull becomes even more mysterious. It holds galaxies together against the tide of a universe accelerating toward openness, shaping islands of structure in an otherwise dispersive sea. This quiet persistence, fragile yet enduring, reveals that existence depends on balance rather than dominance. Too strong and the universe collapses. Too weak and it never forms. Gravity's weakness is the narrow doorway through which the cosmos steps into complexity. It is the soft threshold that allows stars to burn long enough for life to awaken, and matter to arrange itself into observers capable of asking why the universe is this way at all. As we stand at the end of this exploration, the emotional weight of gravity's faintness deepens. We inhabit a world suspended between forces vast and subtle, held to the surface of our planet by a pull so gentle it barely registers. And yet, without it, no star would shine, no galaxy would swirl, no consciousness would rise. This fragility is not accidental. It is woven into the structure of reality. And this invites a final question. If gravity's weakness reveals so much about the universe, what else might lie just beyond its quiet pull? We look upward from a small world, anchored by a force that feels almost like a whisper, into a cosmos so immense it defies imagination. We have traced gravity from the heart of quantum uncertainty to the swell of cosmic expansion, from hidden dimensions to emergent geometry, from fine-tuned constants to philosophical reflection. Each step has shown us not an answer, but a doorway. Gravity's gentleness opens toward realms we have not yet touched, realms where the true laws of existence may wait with infinite patience. And so the journey ends where the horizon begins, with the possibility that the greatest truths still lie beyond gravity's soft influence, waiting for the moment when we are ready to follow its faintest clues into the deeper structure of reality itself.